Okay. Good morning, everyone. Okay. Uh, I think I mentioned that next week Thursday quiz. Okay. It will be introduction, the autonomous differential equation, separable equation, and linear equation up until there. But on today's class, I would like to maybe continue a little bit. So after linear equation, we have something that we call the exact equation. So maybe just a little bit intro for today's class. And then next Tuesday, we will continue exact equations and then giving you some sort of practices, exercise on how to use. I think maybe we can also exercise with the separable, linear, and also the exact equation. So let me start with the exact equations. So let me write here. Remember in the partial derivative when you learn in calculus 2, so if we let some, let's say z as a function of two variable x, y, we can partially derive this and make z becomes dz, and then the fxy becomes, we use the Leibniz notations, dou f dou x dx, right? And then plus dou f dou y dy. Okay. And if the function equal to 0, it means that this whole thing will be also equal to 0. Okay. Now, if we have some functions, for example, if we have, so example here, if we have x squared minus 5xy plus y cubed, and this is equal to a constant, okay. Now we partially derive this functions. It turns out that we have, so we partially derive with respect to x. So we have 2x minus 5y, and then multiply with dx, and then plus, we differentiate with respect to y. So we have minus 5y, 3y squared, or 3y squared minus 5y dy, and it is equal to 0, right? So the idea is, how can we recognize that from this is differential equation, right? So from this differential equation, can we reverse? Can we make it backwards? And perhaps, can we make this dE equal to So that's the idea. So we are going to focus on a differential equation that is precisely, the structure is like this. So we have something on this dx. So we have some equation here, and dy is some equation here. Okay. So that is the structure for general exact equations. Okay. So we call this an exact differential. So we call it, this is exact equation if we can make a structure that can be groups as dx and dy, and you will see in each groups they have a function of two variables x, y. Okay. Now our goal from this exact equation, we are going to reverse, okay, and make it into the solution. Okay. We want to make our solutions. Okay, and then if we write here, let's write the m xy dx plus n xy dy. Okay, we can rewrite this as dou f dou x dx plus dou f dou y dy. So we know that the m is actually the partial function of f with respect to x. Okay, and also n we can write as so if you remember when we did the calculus 2, if we take, for example, f, we can make fxx, right? We can make fxy, fyx, and then we have fyy, right? It means that it's the second order, or it's second derivative, right? So we first derivative with x, and then the second one also with x. The first one is x, y, and then y, x, y, y. And then from the proof in calculus 2, we know that this xy is equal to yx, right? So it means if we derive this with y, it will equal to this derived with x. Okay. So let's write that. Let's write first. So if we take m and then we take derivative with respect to y, we get that this will be, let me just write completely here, that this is dou f dou x, okay, and this will be equal to, we can write like that, and this will be equal to dou x of the dou f dou y, and this will be equal to dou n dou x. Okay, so at the end we get that dou m dou y is equal to this. Okay, so a necessary exact differential, okay, or criteria. Okay, so first we need to have a criteria for that function to be exist. So the criteria, we want to make sure that when we partially derive the m with respect to y, it's equal to this n derived with respect to x. So we need to make sure that this is equal. And then if that's equal, then it's the first step that we can use the exact equations. If not, then perhaps there is no function exists for such criteria. Okay. Okay. So I think this is just important that the necessary and sufficient condition for the exact equation or differentials is this. Okay. Now this term is just assumption that we usually have continuous functions in a defined interval and so on and so forth. Yeah. Okay, now how we use the solution, okay, or how we use the method to obtain a solution. Okay, I will take the new page, but okay, let me check first. Sometimes we call this equaling these two criterion. Sometimes we call check the exactness. So if it's just asking check the exactness, then you need to just equaling these two, and if it's equal, then you say, oh, it's exact. If it's not an exact differential, or it's not exact equations. There is some method of solutions that, in general, by default, it's also explained in the textbook. But I would like to try and using the real functions, so that I believe it's easier to understand. Okay, let's say we have we have that. So we have we check first. Okay, we check first. So first is check the exactness. Okay, which means we determine this one is m, this one is n, right? So that means this one is the dou f dou x, this one is dou f dou y, right? And then check the exactness. So we are going to take derivative partially derived with respect to y for m, or the dou f dou x. So we are going to partially derive this. Okay, that's our results. And then take another one for the n. And we see that I think it has different results. So it's just negative half sine y. So it's not equal, right? It's not equal. So we can write here that the dou m dou y is not equal to dou n dou x. So it is f, or the equation is not exact. And you could imagine, to make it exact, I think we can just remove 2 and it will be the same. Okay, let me start with the method. I think let me give you the general idea first. So method of solution. So given that we have this plus n dy equals 0. Okay, suppose that this is exists, or let's say exists function of two variable xy for which the dou f dou x is equal to m. Now let's integrate this. Okay, let's integrate. And then becomes, and taking the m, we take the integration with respect to dx. But we need to have a plus something, right? Plus something. So since it's partial, so if we imagine we integrate a partial derivatives, so another component that should comes out is a function of the other variables. So if we try to derive with respect to x, and then we integrate, then it will perhaps adding plus some kind of function, but with y as a variable, right? Okay. Because remember, when we derive with respect to x, we treat y as a constant, right? So we could maybe establish this g. We can write is the, let me write with the code, is a constant of integration with respect to dx. Okay, although it's not really official definition, but I can say that it turns out like a constant, right? And then what's next? What's next is from this supposed to be f. Okay, we are going to, let me write here, partially derive with y. Okay, so we write down that dou f dou y, it means that we are going to partially derive all that, so integrations of m xy dx, and then since it's a function of y, this becomes g prime y. Okay, means the first derivative of g with respect to y, right? And then remember, these terms mean our n, right? So this will equal to n. Okay. And then we can rewrite we can rewrite this. Take the g prime y. So we have n, and then minus now to prove that this is true, it means that if we derive this with respect to x, okay, so let's take derivative, partially derive all the g prime y, we need to make sure that this will result in 0. Okay, so if we did that and it's 0, then we prove that it's true. So we have dou n dou x minus dou y dou y dou x m xy the x, or we get dou m dou y equals 0. Okay. Now another way, so this is if we take the m, right? This is the m root. We can also make the same argument with n. We can make the same arguments with n. So let me write here as an alternatives. Let me make it smaller a little bit. Okay. So let me write alternative. We can take the f and then using the n. Okay. The n is dy, so we are going to get function of x, okay. And then we get the h prime x, which we can rewrite as this. Should be n x y dy. And then you could also do the same argument, and then we can make sure that if we derive again, we get the same expression. Okay, I think still abstract, right? So let's try some functions. Okay, let me write. So let's suppose that we are going to solve this equation with exact equations. The first thing we do is we check this m and n, and we take derivative partially both sides. So dou m dou y is 2x, and then dou n dou x is also 2x. So they are exact. So we can go for the next one. So or we can write first equation is exact. So there is a function f(x, y) such that this is 2xy, and dou f dou y is x squared minus 1. Okay. The m and n. Okay. Now if we are using this one, then if we integrate, let me write integrate with respect to x. So we get f(xy) let me write first like this, plus g of y, and this is becoming, so we are focusing only x. Okay, so we have the x squared, y, and then plus g of y. So this is, so it's like we making some trial. Okay, okay, we have an offer this function. Okay, and what do we do next with this function? We are going to derive this. We are going to derive this with respect to y. Okay, so we derive that, and we get that dou f dou y is x squared, okay, plus g prime y, and this is equal to n, right, which is x squared minus 1. So it follows that we have g prime y is -1, right? We solve this equations, which means that perhaps this g of y is just -y. So we have another proposal for our solution, that is perhaps the solution are x squared y minus y. So solution in implicit form, we can write x squared y minus y equal constant. Okay. And then we can see that we can rewrite this. So x squared minus 1, so it's c over x squared minus 1. And remember, we need to define the solution as well. So define on all r except 1 and -1. Okay. So and we can also try with another. So this is for m, right? We can also try for n, and basically similar process, step by step similar process. Okay. Okay. So first thing, check the exactness. Okay. So check m and n, derive both m and n, and if it's equal, then we can go through the exact equations. And then basically, I think if you are maybe nervous or maybe somehow not really remembering the formula, you can try to rewrite the partial derivative. You can to write the partial derivative, and then every time you see this kind of functions like this one, this differential equations, this is actually, you can think this is like a partial. So this is partial f(x), this is partial f over 1. Okay? And then the next thing is we make sure that they are equal when we derive with respect to y for m, and derive with respect to x for n. Okay. So if you want, and then you want to try, for example, we try the x, right? We try the x. Let's try the n. Okay, let's try the n. So the n, if we try, let me write here. So integrate with dy. So we are going to have our f, or maybe let me write with green. So f x y equal, integrate this, right? And then we have plus h, now x, okay? And then this becomes x squared y minus y, and then plus hx, right? And then take the partial x, okay? So we have dou f dou x is equal, so we take the derivative with respect to x. So 2xy, and then this will be 0, right? And then plus h prime x. And then this should be equal to 2xy, right? It's equal to 2xy. So h prime x is basically or let me write down here. So 2xy plus h prime x is equal to xy. So h prime x is equal to 0, right? So hx is a constant. So is this correct or not? Okay. Okay, I think it's correct. So fxy is x squared y minus y plus constant. Okay, but we're not sure what's constant, but pretty sure that we see that it's kind of similar, right? It will be, I think, a better correct result if we know maybe the initial conditions. Maybe they will have a similarity. So we have this for the left side and this for the right side. Okay. Any question first? And remember, the solution should be in the form of, for example, fxy equal a constant. It means that you need to write like this. particular constant. I think because this constant is also constant, then there's no formula. But I think maybe to make sure that our idea is still the same, let me just write 1, okay, just to make sure that maybe they are different numbers. But we are not sure if we haven't checked any initial value problem. If we have maybe initial condition, maybe we can make sure that they are equal. Okay. I think for today that's all. Okay. I think for today that's all. Any questions? We are continuing the exercise next Tuesday for more practice with the separable, linear, and then the exact equations. And the next Thursday, a quiz, okay? So I hope everyone come to the class. And then to end our lecture, I would like to have a post-test, I think as usual. Okay, so go to joinmyquiz.com and enter the game code. I think we have tried once, right? So this is the second one. I hope you still remember the autonomous DE. I forgot I prepared maybe two or three. I forgot 2 or 3 questions. Use your student ID, okay? Use your student ID. Do not use your name. Okay. I think one question needs some calculation. I hope you're ready for that. Okay, I think we can start. All right, we can start. they are using Slido and Inventor software. They use five more students, five Okay, all done. Okay. Okay, it's true. Okay, that's the question. I already given you the solution formula. You can determine based on the template that I gave you. Another way is just to check some random numbers and then differentiate and make sure that it's equal to the questions. But I think it takes time. Yeah, you can check the numbers if you don't want to take the integrations. I was prepared giving you multiple choice for this, but I think if you are clever enough, you will check one by one and then you will get the answer easily. Yeah, this one should be separable equations, right? Move out the y to the right. Simple integrations and you look at the result. And then check 0, x equals 0, and y equals 5 over 2. If you want, you could also try using the linear equations, but too much time for them. I think it's separable. It's solved directly. You can separate and then integrate.